Hello, everyone. Welcome to this week's Crunch seminar. Today, we have two talks. Our first speaker is Dr. Shervin Parsi, who got his PhD from the City University of New York. And today he's going to talk about a little bit about his research. Shervin, with this short introduction, you can start whenever you're ready.
Okay, great. Thank you for having me. I'm going to talk about thermodynamic of learning probabilistic models, and you can also call this thermodynamic of training neural networks. And because this is an unusual way to study machine learning problems, I need to tell you what's the motivation to apply thermodynamics first. So the question that we want to answer is basically the question of how to measure information in a neural network. After you train your neural network on a training data set and your neural network is doing a good job in the test set, the question is that how much bits of information your neural network learn. And it would be ideal if you can measure this information during the training process, kind of evaluate your neural network. And a natural question is that where to look for this information? Is it in the weights of your model or in the activation of hidden layers? Or is this a Shannon information that we can use entropy to measure it, or is it a different type of information? And at the end, we will talk about what to do with this information, or what insight we can get from this information. So let's review some of the work that people did on this topic. And this is a very old problem. And this paper is from 1993. It's a great paper with Hinton and Van Kapp. So keeping the neural network simple by minimizing the description length of the weights. So what they showed in this paper is that weight decay regularization is equivalent with minimizing the entropy of parameters. This is a huge observation, and I think it's one of the findings that's overlooked over these years. So let me explain what this means. Weight decay regularization means it is what you use to avoid overfitting, right? We do weight decay regularization to avoid overfitting, and overfitting means the time that you learn too much from your training data set. You don't want to learn too much from your training data set. This is saying that to not learn too much from your training data set, you need to put a constraint in the entropy of your parameters. That means this is the parameters that are holding information. So the entropy of parameters is a measurement of information in your neural network. So that's the first view, which I like it most. Information is in the weights of your model. Now, the second view, which is this Naftal and Tishibi paper. It's a great paper. It's one of the pioneering paper. It attracts tons of attention, many follow-up paper after this. But the way that they compute information is problematic. So let me tell you first what they did. They measure information between input layer and hidden layer, and output layer. So this was a classification problem, and output layer and hidden layer. And they basically show that you are going to a phase of data compression, that this mutual information between X and Z is going to decrease in second phase of training. And that means that your model is going to discard some bits of information about the data. And this is good because it's going to make your model to generalize better to predict labels on test data set. And they said that the best match for this is information bottleneck. So they didn't show that information, the minimization of classifier loss function, which is a cross entropy, is equivalent to information bottleneck. They just said that, look, this compression of data can be explained by something similar to information bottleneck. Now, why this is problematic? First of all, this mutual information is ill-defined because Z is a deterministic function of X. And that means that this mutual information is infinite if X and Z are continuous. So that's the first issue. The way that they address this is saying that you can think of some noise in your hidden, you can add some noise to your hidden neurons activities, but that's going to change the problem completely. That's not what we do in machine learning. Or they refer to the noise that we have in a stochastic gradient descent, and they explain that due to that noise, Z is not actually deterministic, but that's also not valid because the stochasticness in your SGD is the stochasticness of your parameters. And still Z is a deterministic function of X. So that's the first issue. The second issue, which is also true for the first paper, is that there is no way to calculate this mutual information because you need to know the joint distribution between X and Z and the marginal distribution. This is also true for the work with Hinton and Van Kamp. Again, if you want to measure the information in parameters, you don't have access to distribution of parameters, and you don't have access to the joint distribution of parameters in your model. So so this is a challenge for both approach. So this is the second flavor.
Can I say something here?
Yes, yes.
Because the moment you define a norm, let's say L2 norm, you assume a Gaussian distribution. If you define a L1 norm for minimization, you assume for the data, and I think the parameters, you assume a Laplace distribution. So is that an automatic choice?
I'm not sure about this. I'm not sure about this. What I know and what I learned from this paper is that with the L2 regularization, you're minimizing the entropy of your parameters, and the entropy of the distribution of parameter appear as a Gaussian, as you said.
Yeah.
But I'm not sure if you change it to L1. I assume
that's a Laplace. It's a Laplace. You can show that's a Laplace.
It's gonna have the same effect probably.
Yeah.
Yeah.
On the second on the THP.
Yeah.
So are you sort of disputing the notion of dividing the network into encoder-decoder? Because the X to Z1 is an encoder and Z1 to Y is a decoder.
Yes, I kind of, so it depends. In this neural network structure, I think that's not a perfect picture, because again, Z1, Z2, Z3 are deterministic function of your input. So it's a map. I think what you learn is when you have a stochastic map from your data. So let me give you an example. If you think about variational autoencoder, the latent space of a variational autoencoder is a stochastic map of input. So you give the X input, your latent space is a stochastic map, is not a fixed deterministic function from your input. And then you use that latent space and you use a decoder to generate what you need. So in that picture, the encoder and decoder picture works perfectly fine. But here, this Z1, Z2, Z3, so based on information theory, you are not changing any information. You are not doing any information theory, at least in the sense of mapping X to Z1 and Z2 and Z3.
Okay, thank you.
Okay, so that was a very good question. And the last view is the end of the spectrum, which is that we are just wasting our time. There is no Shannon information. And interestingly, this also has many followers. So this is one of the paper I find. So in this view, we think of the information processing in neural network as a kind of geometric information. Or maybe this is related to what you said just, George. So the neural network is not handling the Shannon information, but rather just mapping a vector from one space to another space. And once you do that, because the dimension of this space is different, you sort of changing information in this vector. But I should say that this word information is not the Shannon information. The Shannon information is about a stochastic random variable. So we should keep this in mind. So you can say you are projecting the information of a vector to a new space, but that's not the Shannon information. It's a different information. Okay, so that's the tree flavor. And there are more recent paper on this topic, but these three kind of summarize what we know so far. Okay, now what I want to say in this presentation, which is based on my recent paper, is this: at least for a probabilistic model, information in neural network is the Shannon information. So first of all, this is the Shannon information, and it's stored in model parameters. So I'm advocating for what also Hinton said. It's in the parameters, not in the activation of hidden neuron. And more interestingly, it can be computed as entropy production of the training process, which I'm going to talk about. Okay, so now let's get kind of more concrete, define some notation, and say what exactly we want to do. So by probabilistic model, I mean this: given a set of observation from a random variable B, I call this random variable the ground truth random variable. This is where you sample your training data set. You learn a probabilistic model, which is a parametric distribution. So you use a neural network to build this distribution. And you learn theta such that maximize this log likelihood objective. And what is really important is to note that this encompasses a wide range of machine learning problems, from, I don't know, MNIST classification to current large language model. What you are training is a distribution. Your model is a distribution. And you sample your distribution at the end. That's why they call it generative AI, because you generate sample. So variational autoencoder, adversarial neural network, any of this large language model, they all fit in this category. And so what we want to say implies to all of them. So anytime that your model is a distribution, we can have this sort of machinery that I'm going to show you. So in the training of a probabilistic model, you observe two stochastic maps. The first one is the optimizer of a stochastic map. This is the choice of hyperparameters, the choice of optimizer you choose, the way that you sample your model. I don't know, you oversample your model, you augment data, whatever you do, that's a package, that's your training approach, training strategy. And this training strategy, if you do it on an ensemble of computers, at the end of n-step training, each computers are going to show a different final parameters because of the stochasticness of training process. So that being said, means that your training algorithm, which I call it optimizer map, is a stochastic map. Given the random variable B and whatever is your strategy to train this model, you are going to get a stochastic variable theta, which is your parameter after T step of training. The second one is the inference map. This is the model itself. So this is where you generate data, model generated samples. This is what you use. This sample can be labeled in case of classification. It can be image, it can be token for a large language model. And the main observation here is that the sample that you generate are conditionally independent from B once you have the theta. So given theta, X is independent from B. And that means that you have a Markov chain here. So theta, your parameters, is depend on B, the ground truth random variable that you sample from your training data set. You have a finite number of sample, of course. And X is depend on the theta. By the theta, you define your model, you sample your model. Now we are getting close to defining two important information measures here from the data processing inequality. This data processing inequality is just the natural consequence of this Markov chain, but it has a profound interpretation, I would say, in machine learning that I'm going to talk about. So the left-hand side, I call it memorized information, or M-info. This measure the amount of accumulation of information in parameters about the ground truth random variable B. So that's how much your model memorized about the ground truth random variable. The right-hand side is the kind of task-oriented information. It shows your performance. So whatever is your task, if your task is to generate samples similar to B, for B is the image of cats, you want to generate X similar to cats, this measure how much your sample, generated sample, has information about the ground truth variable, right? So these two measure, these are going to be our two information measures that we want to compute in this process. So here we are getting distance from what Tishibi said. We are not looking at mutual information between our hidden layers and input layers. This is more similar to what Hinton did, that we are looking for mutual information in parameters, and then the sample that generate our model with the ground truth random variable. So let me tell you what this inequality means in this setup. Okay, so I don't know if this is a good idea, but I'm going to explain it by kind of a story from my college time. So whenever I had exam, our lecturers said, for example, we are going to have an exam on chapter 6. This chapter 6 for me was this ground truth random variable that I have to sample from, I have to learn from. And this theta is my studying method, is the way that I'm going to learn. And X is what I know in the exam day, what I can write in the paper. So as a lazy student, your strategy is to make sure that you learn as much as less as possible from chapter 6, but have the right answer in your exam, in your exam day, and X, know what to answer is X in your exam day. So the left-hand side is the accumulation of information from training data set, as how much you learn from this chapter 6 or from your training data set. This is a measure of overfitting. If it's too large, you're overfitting. So you want to keep the left-hand side small. The right-hand side is your performance. You want to maximize this. You want your sample be more, as much as more informative about B as possible. So you increase the right side. And the ideal scenario happen when these two are equal. So your M-info is equal to L-info. In the case of the exam, it means that you know that you exactly learn what is coming to exam.
Can I ask a question? So
Sure.
I think the difference with Tishbi's approach is that you don't commit to specific layers, like you mentioned earlier. But I think you agree that the learned information is related with the upper layers. Maybe we don't know exactly which ones, and that the memorized information is connected with the lower layers, the first layers close to the input. So I think the difference between you and him is that he's sort of giving he's committing to geographic information, as opposed to you that you're committing to data and parameters. And you use but also his DPI is correct, because as you move from left to right in the network, from the input to the output, you're not going to gain information because you're just processing information. There's no new information. So his DPI is valid like that, going from left to right. But also in your case, it's clear that the upper layers are the ones that that have this learned information. I mean, there are many studies, including ours, that we know that, and that the first day, the way you do the fitting is this memorized information. So what I see is actually not a contradiction. I see a parallel, just a different approach. In your case, you don't want to commit to specific layers.
So let me go back and ask you a question. Do you see any difference between the way that Hinton and Van Camp measure information in neural network and the way that?
Oh yeah. No, I do.
So
the statement is obvious to me, because of course you want to penalize the way to be around zero to minimize the entropy. Sure.
But the message is that the information is in the parameters. Here in TSHB work, the message is that the information in the activation of hidden neurons. It's two different things. It's two different measurements. So
if I may say something, in the actually also when you were talking about this part of say, you said that you cannot have noise or in this process because it's purely deterministic. Like C1 will be purely deterministic from X. So you're not sampling from any distribution. There's no probability. But I think that I think it was one of the first papers that he put when he did the computation of the SNR. He doesn't say that you have this noise from the data. He says that the problem is, like, if let's assume you have X, you can divide X into many subdomains, and each one of those subdomains will tell you a different story. Let's assume something simple, right? You are just putting, I don't know, learning something, right? Each subdomain, each set of your data set will try to tell you a different story. If all those stories agree with each other, well, then your signal is high, your gradients are high, because all of them are pushing to the same direction, and then you minimize the problem and you're good. But if they do not agree with each other, well, then each one has pushed in different directions, your noise is high, and then you converge to another point that where you don't want. So what I'm saying with this is, like, even if you are not sampling from a probability, you have noise because each sub-sample, each sub-space of your data can tell some different information, which will induce to different gradients on the parameters. So ideally, yes, you go back to the first point that yeah, the information is in the parameters.
That's the stochasticness of the parameters, not the hidden layer. So you are talking about mini batch. When you get a mini batch of your game data set, each mini batch has a different I don't call it different information, but I call it different vector, different set of vectors, and that's going to have a different effect on your parameters, and it's stochastic on the parameters. Again, I want to reiterate that there is two views, both valid, both have followers. One is that information in the parameters. So if you want to talk about information, you need to go after the entropy of the parameters. The other one is that the information is in the activation of hidden neuron, which I think is coming from a kind of neuroscience background, that we think that these neurons are coding information. But keep in mind, in the context of neuroscience, neurons are stochastic. And again, so as George said, one good example is variational autoencoder. If you have hidden layer that are stochastic map, like variational autoencoder, from your input, that's perfectly a point that you can calculate information and you actually have information. But to me, a deep neural network is just a notation for a parametric function. So keep this in mind: Z1, Z2, Z3. I can write this function in many different forms with exactly same output and input. So this is just a notation, and Z1, Z2, Z2 do not carry information. At least this is what I understand from classic information theoretic point of view. These are not a stochastic variable. So I know that TSHB said that you can do DPI here. So according to DPI, Z3 is less informative about X, Z2 is less informative, and Z1 has the maximum information about, so you're kind of losing information. it's very intuitive and appealing, but again, these are just deterministic function of each other, and they don't carry information.
Yeah, I agree that during evaluations they are purely deterministic, but while training they may not be purely deterministic, right?
During the training,
during evaluation, I completely agree, because then don't tell each other, you're just passing information from one side to the other. But while you're training, every part will tell the difference.
no, the question of deterministic, or so if given X, do I have any error in guessing Z?
Can you, what do you mean?
So given X, if I give you X at any time, either training or prediction or whatever, even X, do you have any error in guessing Z? No.
Any error in guessing C, assuming that is the final C that gives you the best Y, or?
So I'm just saying that Z is completely determined once you have X.
Yeah, C is completely determined, but C at T plus 1 may not be completely determined. No.
Z plus 1?
T plus 1. Let's assume that you have a C of iteration T. Let's see, put T as iterations, okay? So C at T0, let's say that we're in Tn, T equals T, or T equals N. At T equals...
I think these are all the assumptions, because even the Markov chain is an assumption, but it's, so I see what you're saying is, it's true probably for the lower layers, but the upper layers could be stochastic. I don't think data uniquely define the upper layers, because I can take a very, very deep layer and that will not be the case. The Z100, for example, I doubt that that's a deterministic function of your input. It cannot be, because there are, the way you solve the mini batch, the stochastic gradient, and all that, have so much stochasticity that it cannot be deterministic, certainly during the training.
I see.
But I totally appreciate the point of view that you want to take. It's not. I was just trying to say that the two views are not necessarily inconsistent, although there may be technical discrepancies and maybe not so much rigor in the definition of this. Yeah. But so please go on. We don't want to derail from your.
I will continue. I just want to add one thing. So here we can also talk about information of each layer. So I don't have a slide here. It's a follow-up paper I'm going to publish. Hopefully, you can compute this mutual information between B and the theta corresponding to each layer. So this is also possible. So same as maybe similar to what Tishibi did. This is also possible here. But again, it's going to be the mutual information between your ground truth random variable and the parameters of your model. Okay, so there is one observation that can make things more simple for us. And so it's again about the stochasticness of gradient descent. This stochasticness is kind of low variance. That means that it's true that your parameters are evolving stochastically. So this graph is just a toy problem. I'm looking at, I think, 3 parameters that they are evolving with 3 different mini batch size. So mini batch size 1 has the maximum value of stochasticness, and you increase the batch size and you reduce the noise. And the point is that it's true that it's stochastic, but it's confined to a very small region. So this means it keep it very low variance. That being said, it means that the accumulation of mutual information between B and theta is mainly correspond to the increase in entropy of your parameters. So the big part of, so to the change of this is mainly due to the change of entropy of parameters. And there's another notion in information theory that we can use to explain, to reduce the this mutual information between X and B to the mutual information between X and theta. and that is the sufficient statistic map. So theta is a map of B, and if theta is a sufficient statistic correspond to the task that you want to do. So let's say that this task is classification or generating image. It means that theta hold exactly enough information from B about your specific task X. If that's the case, which is what we want to do in machine learning, that's the end goal in training your model, then the mutual information between X and B reduced to mutual information between X and theta. It means that at the end of the training, you can get rid of your B, you exhaust B, useful information from B, and the mutual information between X and B is equal to approach to mutual information between X and theta. And so again, this is two information measures that we just defined it, and we are now going to compute them, calculate them in the training process. One is minfoo, a measure how much information is stored in the parameters. This is a measurement of overfitting, as Hinton mentioned. So you don't want the entropy of your parameters to blow up. And the other one is your performance. You want Linfoo to be maximized. That's how much information you learn, and that's the information, the useful information that you can do useful thing with it. Okay, good. So let's start talking about thermodynamic. And I should say that, so I'm not going to rigorously show you the mathematics. I'm going to tell you what's the machinery, but at some point I'm going to refer you to the paper, because the mathematics is simple, but just kind of tedious to show it in the slides. So when you train your neural network, you are generating a series of parameters. This parameters trajectory is the time evolution of your parameters. But the main observation here is that this means that your model is also evolving in time. So each theta defines a model. That means that you have a time evolution of a distribution. In modern thermodynamics, you can describe a thermodynamic process by time evolution of a distribution. So basically, if you have a physical system X, this physical system is surrounded with some environment, which we call it reservoir. The state of this system described by its distribution. That's the main idea of statistical physics. We care about the distribution of X degree of freedom. And the thermodynamic process, by definition, is the time evolution of this distribution. Of course, with some criteria, which we're going to address that. We need to first define what is this reservoir, how can we define the temperature, what are the physics law governing this time evolution, which is the technical part of this work, which is the local balance condition. And then finally, how to compute the thermodynamic quantities and interpret them. Okay, so the main idea is to use this time evolution, and the time evolution of distribution has entropy production, heat dissipation, and other thermodynamic quantities. So about the parameters, we have one good candidate for heat reservoir here, and that's the parameters subsystem. Parameter subsystem is itself a stochastic system, right? It has theta degree of freedom, and it's a huge system. So first of all, there are two criteria for your heat reservoir from thermodynamic literature, one of them here. The first criteria is that your reservoir should have a self-equilibrium property. It means that it's no one should say to your reservoir what's the equilibrium point. The reservoir itself should have this property to go to its thermal equilibrium. And the parameters naturally have this because you are minimizing the loss function, and you can look at the loss function as a potential function. So it's naturally drive your theta subsystem to equilibrium point. The second one is high heat capacity criteria of a reservoir, which is a kind of a thermodynamic explanation of why an over-parameterized model can benefit us. So that was one of the mystery of machine learning, which has been addressed in many ways, but this is a thermodynamic insight of what can be the benefit of working with over-parameterized model. The benefit is that the heat capacity of your theta is huge, and that's one of the criteria of your reservoir. And finally, once you have this, you want to talk about the temperature of your reservoir, and that's coming from the noise ratio, the ratio between the stochastic force to deterministic force in the dynamic of theta. So the classic way to do this is to write the stochastic gradient descent in the Langevin form, and then use the dissipation theorem to define T. Saying that, I should say that it has been shown that stochastic gradient descent does not satisfy necessary dissipation theorem. That means you are working with a reservoir which doesn't have a very well-defined temperature. At each part of this big reservoir, this deep neural network, you might experience different temperature. And temperature means the noisiness of parameters, which is true.
Can I ask a question here? Because if you're in equilibrium, which is your first bullet, then the dissipation fluctuation theorem will hold.
With the first optimization steps, right?
Yeah. I mean, at equilibrium, if you are far from equilibrium, yes, the dissipation fluctuation theorem will not. But if you do, then the fluctuations and the dissipation are related.
I agree with you. I agree with you. So,
Okay.
so exactly this is the way that I discussed this in the paper is as follows. I said that we are going to think about kind of naive assumption that this reservoir is perfect and is in the equilibrium and is fluctuating. Then a dissipation theorem, you can perfectly define your temperature. But more realistic scenario, as you can see in machine learning, you train your machine learning, the loss function drop, everything is good, and suddenly you get a jump. You get a bunch of jump. So that's just very abrupt change in the dynamic of your parameters, the state of the potential function that define the equilibrium state of your parameters. And those kind of spikes are very difficult to explain by fluctuation around equilibrium. So I would say the problem is richer than this, but you are right. At least at certain interval that your loss function is fluctuating around a certain value, we can definitely use that. Okay, good. So far we have a system X and a reservoir. Now we are going to get kind of pause from doing machine learning and review one very important lesson that we learned from thermodynamic over last couple of years, which these days known as thermodynamic of information. So what is the second law? The second law is telling us that if you have two subsystems, which is the thermodynamic process at least have two subsystems. One X is a system of interest, one theta is the reservoir. The sum of change in entropy of each system adding together is always bigger or equal to 0. And if this theta is, let's say theta is your reservoir, the change of entropy in the reservoir is the heat that reservoir get from your system, assuming that it's a perfect reservoir and it doesn't do anything except exchanging heat with you. And then entropy production is just basically the left side of this inequality, and it's a sign of reversible or irreversible process. If it's 0, it's reversible, and if it's bigger than 0, is irreversible. Now, the big finding of last few decades is this. the entropy production causes accumulation of mutual information among two subsystems. And there are many ways to show this. These two papers are here for your reference. This second one, they use fluctuation theorem to show this, that entropy actually measure the mutual information between two subsystems. And the first one, I guess they use the definition of KL divergence. They start with free energy and the KL divergence to show that. But I just want to tell you that you can see it right away. What is the definition of X? What is the definition of mutual information? It's entropy of X plus entropy of theta minus entropy of joint. So the change in mutual information is this two term minus the entropy of joint. And if the entropy of joint is conserved, it means that the change of entropy of joint is conserved. Either you can call it conservation of information, or if you want to do physics, you get Liouville theorem. Then this two change is basically the amount of increase in your mutual information. Now, what this means, let's think about a very basic problem. Let's say that we have a cup of tea in a room. The cup of tea is a system of interest and the room is our environment. When tea is equilibrating with the room temperature, this is of course an irreversible process. Basically, the second law is saying that in this process we have entropy production is an irreversible process, sigma is positive, and the amount of entropy production is the number of bits that this cup of tea share with your reservoir. So you do have irreversible process when two subsystems learn from each other. Again, if the entropy production is zero, you exchange information. It's like that you have a file and you pass it to the other person, you no longer have that information. You just exchange the information. But when you going through a irreversible process, you're sharing bits of information. And so that's the main message of, that's one of the finding of modern thermodynamic of information, which is connecting thermodynamic and information theory. So we want to use this naturally, right? We already have a system X and theta. X is my sample that I'm generating from the model, and theta is the parameters. And this is where everything comes together. So maybe we need to spend 5 minutes in this slide. So we have a system X. This system X is evolving, and the sample that I'm generating from this system is the microscopic state of this system, is my model generated sample. That's what I'm using. For example, if you want to think about images, at the beginning, your system just generate noise, and at the end, you gradually get the pattern, and at the end, you get the perfect image of human face, for example. And theta also has the initial distribution. Theta is also evolving in time, and these two subsystems evolve in contact with each other, and the entropy production happening in this process is the accumulation of mutual information between them. And this is how we can compute them. So in a very general way, I can write a probabilistic model in this form. This E theta is the function that you usually use your neural network to parameterize it. So you usually learn E theta, and then minus log of E theta is your distribution. Your optimizer take one step to update theta T1 to theta T2. This changed the energy escape of your system rapidly. That means that you are doing work on your system. And the amount of work can be computed by changing average energy of your system with the new energy function minus the old energy function. And immediately after that, your system is out of equilibrium. Now, To do the next step of optimization, to go from theta T2 to theta T3, what you need to do first before doing gradient, you need to compute your loss function. And to compute your loss function, you need to generate fresh sample from your model. And generating fresh sample from your model means thermalization. You thermalize your model, so you take this time for your model to equilibrate, to go back to its equilibrium position, which is a new distribution, new state. And in doing so, the model dissipates heat. And this heat dissipation can be computed as follows. Heat dissipation is basically the change of energy due to change of distribution. Change of energy to the change of distribution. So with the same energy function, what is changing here is the distribution, and the amount of change in energy is the dissipated heat. And the main message is that the amount of heat dissipation is proportional. So actually, this is a strong condition. Equal means that the entropy of the system is not changing. I should update this to proportional. It's proportional to accumulation of information between x and theta. So this is the machinery I'm going to use. Maybe it's a good time if you have any question.
Do we have any questions from the audience?
Okay. Yeah.
It looks like not. You can keep going. Thanks.
Yeah. So let me show you some results, and then we will go through more questions if it was. So here I'm going to compute these quantities for this MNS classification. It's a very simple problem, I know, but it's enough for this purpose, showing just the concept. But this is a generative classifier, and I just want to make sure that everyone knows what is a generative classifier. So the usual classifier that you use is you are learning a conditional distribution. That's called discriminative classifier. In the generative classifier, you learn a joint distribution and basically a joint, a marginal. And the ratio between the joint and marginal is, of course, your classifier. So it's two different ways to learn this conditional distribution. It has been shown that the generative classifier are more robust and they generalize better, but of course, computationally more expensive. Okay, so the model learn, this is the accuracy of the model. This is the loss function. This is the insight that you have from classical machine learning. You look at the loss function, you look at your model accuracy, and the left side, the right side is the information thermodynamics insight, right? So here I'm computing heat and Q and sum of them with the green line for the joint distribution. So this joint distribution has a joint energy function and heat and Q for the marginal one. And here I also plot heat dissipation from X subsystem and heat dissipation from joint subsystem. And the interesting observation, which I know match with what Tishibi showed, is the compression of data. So as we said, the dissipation of heat minus QX measure the accumulation of information between X and theta, which we define it as L info. Is the learned information, is what you learn about your data. And in the first phase, both minus QX and minus QXY increasing. And at some point, your system start unlearning about your X degree of freedom, basically.
So you have the sorry. So that's your inflection point, like Tishby has in the information plane.
Yes.
But there is a compression information, and there is, but in different coordinates. That's what you're saying.
The compression is here. The second phase, you are unlearning basically your marginal model when Q minus QX is decreasing.
Right.
So you're right, that's a main observation, same observation, but I should say that we are measuring different things. This is measuring information in the parameters. That's measured information in the hidden neurons. And again, I want to repeat that I think there's one paper with a group from Harvard. I think they show that if you just change the activation function, this information plane change. So so what you see in the TCB work might not be robust in each scenario. But I don't want to make any claim about compression of data. Actually, that's not my goal in this presentation, or say how this model works. But rather, I want to show the power of this thermodynamic machinery to get insight about how information evolve inside the neural network. And that's the main message of this work. It's a means to measure information inside the neural network.
Okay.
Yes, so I'm officially done. I'm looking for your question, if any.
Okay. Oh, okay, Shervin, thank you so much. It was a really nice talk. Do we have any questions from the audience?
Let me ask, maybe I will start the question. So in practice, we're interested in the size of the network. And also when I do transfer learning, I need to know which layers I have to freeze, which are related to the data, which are related. So having so I think you demonstrated that this thermodynamics is thermodynamic analysis is not complementary, maybe the right way of analyzing, but then I don't see how I can change my network. I cannot see which layers contribute to what. I cannot see, if I don't have this, I call it, let's say, geographic information, how to do transfer learning, because so in our recent paper, that Juan is one of the co-authors, we actually find that the first layers and the last layers and the mid layers communicate different information. There's a binarization of information in the mid layers, and there is a the fitting associated with the lower layers, and the generalization that's associated with the upper layers. Again, I don't see actually anything inconsistent with your analysis. It's just that it doesn't provide me with a tool, unless maybe I can go and look at this QX and this the work and the heat, the dissipation, and see which layer contributes. Maybe I can find out how do I, I mean, basically at the end of the day, you need to tell the people how to configure their networks.
You need to show it. So I totally agree. This presentation is based on the first paper, which is mostly discussing the physics part, that the technical details that you need to do to compute this information correctly. But we need to apply it to deep neural network, and as I said, you can compute the heat dissipation of each layer. So this is going to be so I do have the result, but it's not published. So what we are going to see, basically, you can see two different things. One, you can train a model with a feed-forward neural network and a model with a convolutional neural network. So two different structure, and then you look at heat dissipation, which measuring the amount of information that you learn. what you see is that the slope of heat dissipation with convolutional neural network is much, much higher. It means that the convolutional neural network dissipate heat much, much faster. So this just gives us another way to see why convolutional neural network do a better job in capturing data. Second thing I want to say about this second paper that is coming, hopefully, is that when you do layer by layer, what you see is that the heat dissipation of the last layer kick off at the first place, and the other layer are coming after that. So the first layer does not contribute to learning much at the beginning. And so exactly based on similar to what you say. So you see that here the heat dissipation starting, right? For the first layer, it's flat, it's not starting, and it's a start from the last layer, and then one before that last layer, and it's coming to the first layer. So it's even show the order of the contribution and the amount of contribution of each layer. So it's kind of like extracting the neural network. But you're right, I don't have the data. This presentation was more showing the machinery and approach. Yeah.
One, I saw you put on the archive your paper, but maybe if you can open it on that figure 8, whatever it is, when we do the binarization of the
Okay. Sure.
greenish color. Maybe you can show Shervin what we mean.
Yeah, sure. Let me. If I may share my screen.
Oh yeah.
Thank you. Where's this one? Yes, it's right here. This is like the part when we were computer, like they come.
No, just show the color picture. This one.
This one?
Well, yeah.
Yeah. So essentially, you're seeing that when we call this total diffusion is like in the later stage of training. In this total diffusion, we observed that the SNR like was like reached to some kind of a plateau, and you have like this kind of like nice balance between the noise of the gradients of your parameters and the mean of the gradients of your parameters. And then you see that when you reach this kind of plateau, the layers start to become somehow binary, and that's what you can observe like in the first stages. When you're fitting, everything is like continuous, and when you're in the diffusion stage, everything becomes like binary.
See, very interesting.
So unlike maybe you can show the sketch. You go to the sketch. Unlike PHP, our theory is a little different. It's not 2 phases. It's actually this one here. There's 3 phases. So we represent everything in terms of this signal to noise ratio. So PHP is talking about fitting and diffusion. But actually, what you were seeing at that plot was a total diffusion. When you actually, so the generalization is really the total diffusion. The generalization phase is total diffusion. You can have diffusion, but you still have this memory effects, like you said. But total diffusion is where you actually start generalizing, and you see the convergence of the error too.
So the total diffusion is after the plateau, or it's during the plateau?
A total diffusion is when you reach this kind of plateau, like when you have this nice balance between the noise and
when you balance again, you see there are 2 types when you cross 1, right? This is the SNR is between the mean gradient and the fluctuating gradient, right? The norms.
Yes, so, I think the diffusion is here.
Yeah. So the second time when you cross that 1, you have the beginning of it. So I believe there is a connection to what you were saying, but maybe if you look at our paper, you could sort of break down the stages to different periods of learning.
Yeah, definitely. if one of you can send it in the chat or.
Yeah,
Sure,
I
put it. I put it in the chat.
I see. I got it. Yeah, I would definitely.
Yeah. And also another thing that you said that, for example, this would make sense if you had like batches. But for example, in all these cases, we were training with full batch. It's not batches. So we will training with full batch. We only did the computing DSNR. To compute in DSNR, yeah, you sample some IID samples, and then from there you compute.
Okay.
Yeah.
There is an effect of stochasticity coming in through the mini batch also, and that's. But anyway, that was an excellent talk. I really like the deep thinking, and I'm looking forward to your second paper.
Thank you so much. Thank you for having me. Yeah.
Oh, okay. Thank you so much, Shervin. It was a really nice talk. We have a second speaker today, Yue. I don't know, Yue are, I think I saw you here. So I made you co-host. Yeah. Oh, first of all, thank you so much for joining. I know you're from Chongqing University, so that's a bit far, so I think that it's gonna be a bit later. Okay, so do you want to share your screen?
Yeah, sure.
Okay.
Can you see the slides?
Yes, we can, but they're like compressed. Yeah, no, it's not that good. Yeah, now it's good. Okay. Well, now we have the second speaker. His name is Dr. Yue Qiu, who is currently an associate professor at the College of Mathematics and Statistics at Chongqing University in China. He obtained both his bachelor and master's degree on automatic control from Northeastern University in China in 2019 and 2011. He then moved to Delft University of Technology and earned his PhD degree on mathematics in 2015. He performed his postdoc training at Max Planck Institute of Dynamics, Complex Technical Systems, and he started his academic position first as an assistant professor at Shanghai Tech in 2019. His research lies in uncertainty quantification, scientific machine learning, and the interdisciplinary section. With this short introduction, whenever you're ready, you can start. And once again, thank you so much for your time today.
Okay, yeah, thank you. So thank you very much for having me here. It's my great pleasure to introduce part of my work. Before the talk, I would like to say, so since it's already 1 in the morning, so if I react a little bit slow for your question, please kindly remind me, or if you are not satisfied with my answer, and please write me emails. Okay, so today I'm going to talk about the operators learning for PDEs. It's a joint work with my graduate students at Shanghai Tech. So to start my talk, I would like to motivate a little bit, since we are the group here is pretty expert in this deep learning for PDEs. So that could make my talk to step into pretty fast. So actually, my focus on deep learning starts with the paper by George, the Pins paper, and then. But since my research is a little bit the other way around. Since so I first have my problem, and then I found that okay, it could be a perfect match to use deep learning to solve my problems. So my talk has 2 parts. The first part, I would like to introduce our recent work on this resolution invariant deep operator. And the second part, so if I have time, I suppose I have, I would introduce the Cooper operator learning using invertible neural networks. So the first part, actually, it's when George invites me to introduce my work, he focused on this part. So this part is kind of application driven, since my research part activities focus on these Bayesian inverse problems and uncertainty quantification. So the basic background is that we are often interested in the posterior distribution for the PDE inverse problems. And this posterior distribution is often high dimensional. And since the many complicated PDE problems, their posterior distribution cannot have analytical form. So often we need to solve it by sampling. But for this high-dimensional posterior distribution sampling, it's pretty challenging due to this high computational cost. So we need to simulate or run the parameter to observe map quite often, and this makes the computational cost pretty huge. Therefore, that we need to design this computational chip methodologies to reduce the computational complexity. And the other another important feature is that the quantities of interest, their domain is often different with the domain of the PDE solutions. Take an example like the boundary inversion. Like when you want to infer the boundary conditions or the parameters on the boundary, but often your observables or your observed data, they lie in the inside the domain of the PDEs, and this often this is a very practical scenarios for this PDE constraint inverse problems. So therefore, our motivation for this part is the first is that can we make this computational cost cheap? And the answer is yes. So we can use we can build surrogate models such as the first the generalized polynomial queues proposed by George and his PhD students. And also later with Gaussian process and right now these deep learning methodologies, they are pretty popular. And second is that motivation that how to build a neural network that can learn the parameter to observe a map, while the physical domain and for the parameters and the observable data, they are different. And the answer lies in the fact of the deep operator network. So it decomposes the physical domain of the parameters and the observables. And the third question that, or the third point is that for operator learning, can we use this low fidelity data or data of low resolution to train the network? Because for this, we can easily reduce the computation cost, and we also would like to use this this trend model using low fidelity data for the high fidelity predictions. So for these scenarios, it can makes this computational cost low. So the previous DeepONet fails for this task, but a Fourier neural operator network fits this task. However, when we are concerned with the physical spaces for parameters and observables are different, this Fourier neural network, it fails for this task. So our motivation is pretty simple, and we would like to combine both the advantages of this DeepONet and FNO together to make it feasible to solve high-dimensional inverse problems. So I suppose that the audience are pretty familiar with this DeepONet. Therefore, so I just introduce it pretty briefly. So this DeepONet is a very general framework that it has a very good and a very general structure that decomposes a network into two parts that can easily approximate any nonlinear continuous operator. And this is achieved by designing a branch net and a trunk net. So for this is a pretty generous structure, and it does not require any specific parameterizations of both the branch net and trunk net. And so for this DeepONet framework, it has this discrete inputs of these functionals. The discrete inputs of the parameters, and so this part is kind of mesh dependent. But for the output, it's in a continuous form, so it does not require any mesh information. So for the training that when we want to learn more features or we want our model to have better approximations, and the required or the expectation is that we would like more finer inputs of these parameters. However, this would make this training of this of deep net more expensive since you have high dimensional inputs. So our first thought is that can we make this deep net suitable for functional inputs? And the answer is yes. And when we checked we can just use so-called the discretization operator by just discretize the functional inputs into discrete values. And after we finish this part, we do some literature review. We also found that it's already proposed and studied by one paper, and in that work they call this discretization operator the encoder. Therefore, so with this concept, so it's possible that we can propose a very similar, almost the same structure. So the deep net with that can use functional input, and we can also give the almost the same theorem for the generalized universal approximation for this framework. Therefore, for this framework, it's also a very generalized setting. So it does not require any specific parameterization of both the branch and trunk net. But the only thing that by introducing the so-called discretization operator, it is possible to make the dipole net it can take the functional input. So
excuse me, in the previous slide, please.
Yes.
And the previous. So what is Z?
Yeah.
The last.
Sorry. You mean
Z
this one?
Oh, okay. Yeah. Okay.
Yeah.
So the sensor points. Yeah. The
yes.
Points. Yeah. Got it.
Yeah.
Sorry.
Sure.
Thank you.
Okay. Yeah. Thank you. So by just introducing this very simple idea that we're able just to modify a little bit of the dipole net structure, so that it can take the functional input, especially for the upper part. This is like also a general framework for our model. So for this parameter input, and it takes directly the functional input, and by introducing the other so-called this integral operator in the end of the upper part, so we are able to transfer this the output of the upper part to real vectors. So this T operator it just makes this output of this part to real vectors, since the input and also the information transferred inside this G0 part block, they are all functions. Okay,
can you go over the G0 block?
Yes.
Can you explain the G0 block in a little detail?
Yeah, sure. Yes. So the input is just this a function or the function of the parameters, and so this G0 you can just take it generally as any neural networks that takes functional inputs and also give functional outputs. And this P0 block and the P2 block just maps the dimension of the input and the output. And so inside this part, we use like two kind of different structures. The first part is this Fourier integral operator, and the second is the attention integral operator. And actually, it is not really necessary to use both. And you can just use one, either this Fourier integral operator or this attention integral operator. Why we use both of this here? Just because when we try to run these numerical experiments, we found that by either using this Fourier integral operator or this attention integral operator, there are always some feature missing for this, especially like when we use the low resolution data for training and predict for high resolution, and they are all like this generalization error is kind of a little bit higher. But when we use both, and it can reduce this this generalization error, and actually in theory we cannot prove by introducing the one more block it reduces the error, because in theory it's just a very generalized theory. Okay, I first go to this part. Yes, this theorem, because we are only able to prove that we use like a composition of the integral operator and with any neural operator type of network. By composing these two together, we are able to prove that it also has a generalized universal approximation theorem. However, this is only like shows this approximation, the generalized universal approximation error. It does not specify any kind of detailed about what is composed of the G0 or something. So therefore, for this block, this G0, actually you can just think this this Fourier integral operator or attention integral operator, you can just replace them by whatever kind of neural network model that fits for this with functional input and functional output.
Or Yue, if you go back one again, one slide back. Yes.
You mean previously?
Yeah. Yes. So
okay.
So what? No, when you have the integral operator, I want to the other.
Oh, okay. Yes, so I think it's here.
Yeah. The AIO. Okay. Yeah, that's the AIO. That's basically what you have is the integral. So the kernel is one, right? You know, if you think about FNO, they have a kernel, because that's a very recent paper that Sam Lanthaler, who's now postdoc at Caltech, put on the archive, and he gave a recent presentation to us where he showed that the minimum requirement for a kernel is actually to be a constant one. So it seems that you're using that AIO here for the integral operator.
Yes. Okay, great. So thanks
that is
for
justified by his, that's justified by his work. You can look up his latest paper, you will see. Okay,
good, perfect. Yes, so by just introducing this this integral operator, and we are able to give like a universal generalized approximation theorem. Sorry, my brain almost stops. For our model. Okay, then to summarize or to compare the difference a little bit. This our framework actually it has more like this application is more general, since that it works for the input domain, and the output domain does not require any regular or irregular domain for this. And so for this for this table, and the first 4 rows for our framework and this DeepNet, they are the same. So they are all very general. And the only difference is that since our framework can take this functional input, and therefore, in theory, that it should have this resolution to invariant feature. And since this DeepNet takes this discrete inputs of these parameters, for some problems or for some applications, it may does not have. But since the oh, sorry. But it's also quite easy to adapt this DeepNet kind of to just adapt it a little bit to make it resolution to invariant. But for this Fourier neural operator, there are more restrictions since it uses this fast Fourier transform for this parameterization. Therefore, it requires both the input and output domain should be the same, and also this.
But can I say something? Because
yes,
the paper by Mishra, I think it's called Reno, resolution dependent. So it proves rigorously because that you have aliasing errors. The issue with resolution variances comes down to aliasing, and he proves that FNO is not resolution invariant.
Oh, so, really?
Yes, of course. So the only one that so then he proposes a C kind of like a U version, sorry, like a UNet type in a network that I think I forgot exactly what's the name, but he proves rigorously that neither DeepNet nor FNO are resolution invariant, and that is because of the aliasing error. So you have basically to stack up different resolutions like we do in UNet, and that will give you that then they can prove rigorously that that's a resolution dependent. That's a paper that he presented last year here at Brown in a conference.
Okay, good.
It's on the archive. So I think they call it Reno. If anybody in the audience remembers or they can find the paper, please put it on the chat for you to see it. But yeah, so none of them is yeah.
Okay, good. Thanks for pointing that out. Okay, then we go to some numerical experiments. So the first one is that we are often used for the Yue Qiu problems, uncertainty quantification problems, that we have a PDE with random coefficients, and this coefficients is a random field, and for this test, our aim is we would like to learn the map from this parameter space to the PDE solutions. Therefore, this the domain of this of the input and output, they are the same. So we compare our results with this FNO, and also we would like to compare it with DeepNet. So we found that so for this problem, since it has the boundary conditions is not homogeneous, and for FNO, that without any modifications, we found that it when we train all these models for under low resolution but predict for high resolution, and then this generalization error is increases. But if we just introduce this the hard constraint also proposed in this and also in for the Pin's paper, the generalization error for this FNO can be reduced, and also this our the results given by our model seems to be well, it's not resolution invariant, but like this error keeps in a low level and increases very slowly.
Hello, this is
Yes.
Lu. I have one question about a specific setting here. If we can go back to the table.
Yeah, sure.
So here, the table. So here,
Yes.
when I say resolution 33, let's say when I try to generate a data set. So I drew a mesh with resolution 33. Then I use numerical solver to solve this PDE on using this specific grid, right?
Yeah.
Then when I say resolution, okay. Then when you go to high resolution, CD5, so your testing data set will be the numerical solver using the grid of the size CD5.
Yes.
Okay. I have another question. So let's say if we do have two grid size,
Yes.
so 33 and 65, then when you compare the solution of the 65, let's say whether the solution is the same on the same grid. I'm not sure how to. The two numbers may not be easy to compare. Let's say you have one is 3 point, one is 1, 2, 3, 5 point. Right, so 5 point covers the 3 point. But if you apply the 3 point or 5 point into your solution, let's say for the middle, let's say in your 1D domain from 0 to 1. For 3 point, you have 0, 0.5, 1. And for 5 point, you have 5, 0, 0.25, 0.5, 0.75, and 1. Whether this analytical output, let's say at a location 0.5 is the same or not?
I think they should be the same. And for this test, if I remember correctly, like we first generate all this test data on the finest resolution. Like we compute like the so-called ground truth for this resolution, like 129, and then we downsample this data to make them of a lower resolution.
Okay. Oh, okay. Actually, you go back to my first question. So your resolution for resolution 33, the training data set is not the numerical solver applied on this resolution. It's numerical solver still applied on the high resolution.
Yes, and so I think so. So for this low resolution, the training data is that we apply numerical solvers for higher resolution for this highest resolution, and then we downsample it.
I see. Okay.
Yeah.
Yeah, because in the very beginning you mentioned the low fidelity and high fidelity. So actually here, both are high fidelity. There's no low fidelity here. So the fidelity is always high for the output.
Yes.
Oh, okay. Now I got it. Okay.
Okay. Good. Yeah. So because for this inhomogeneous boundary conditions, and if we do not introduce this hard constraint, so our limited experience is that FNO cannot perform well. And so we also try to test for the other correlation lengths by reducing this correlation length, and this it makes this stochastic more like they are more it makes this problem even more difficult to solve. And we observed that this FNO performs not very consistent. Well, this DeepNet, since the resolution 33 is pretty low, and we believe that, and we also tried that when we increase the resolution of the training of DeepNet, it can achieve a similar accuracy with our framework. But like when we change for different resolutions, DeepNet needs to be retrained. Okay, and also we test for the other problem is that this is also a benchmark problem we take from the paper. So it has like a triangular domain for such problems, and also our aim is that we would like to learn from the boundary conditions to the PDE solutions, and then for this case the standard FNO fails, but in 2022 that the paper from George also introduced they can adapt this FNO a little bit by making it the FNO suitable for such cases. However, we did not have the time to compute the solutions, also compare with that. So we just compare it with DeepNet. So the two tables, the first table that we train and our framework and test our model for different resolutions, and the second table that we just fix the we train and test using the same resolution. And so the late table shows that both our framework and this DeepNet, they achieve a very similar accuracy when we train and test them on the same resolution. And for the first table, it shows that actually when we train on higher resolution but test for lower resolution, and it gets easily like the overfit is more gets more severe. And so it is better like we go the other way around. We train using low resolution, but we predict for higher resolution, and this fits more the scenarios of applications. Okay, and so this is also the benchmark problems, like we add a notch for in this domain, and similar results appeared. Also, this our framework, the generalization error increases, but still the level that it increased is not so high. Okay, so then I go to the second part. The second part is about couple-operated learning.
Can I?
Yes. Yeah, sure. Please.
I think a student of Mishra at ETH, Molinaro, who defended his thesis a few months ago, did the following, and I think you can try that. Since, from my understanding, what you told Lulu is that you run your numerical solver is on very fine grid, right?
Yes.
And then you choose 35 points to do to train the network. But you don't have to use the same. You can basically you can shuffle. You can have different 35 points, keep 35 points, but they don't have to be the same all the time.
Yeah, sure.
So that's what he's doing. That's what Molinaro is doing in the branch. So he would take 35 points, which are different locations. A few of them are in this location, and another few of them are again on 35 points, but different locations, and so on. And by that, he showed that you have DeepNet, which is discretization dependent. So in other words, he didn't change the architecture; he only changed the training. Have you seen that work?
Yes. Actually, so the setting that we used is that we would like to just compare it with the papers. So we just apply the code that we found on the website. So we did not like compare it with this setting. Okay. Like so for some other work, they just take this, like it use numeric solver for higher resolution, and then they downsample it. So we think or we consider this as a standard way for the training. So we just follow follow that approach for the training. Yeah, thanks for pointing that out. I think it's a good point to try this so that it can really make this training for low resolution and then predict for high resolution.
All right, thank you.
Okay. Okay, yes. For the second part is it's also kind of that when we would like to solve complicated PDE problems, and of course one natural choice is that we can use pin or it's related to variant, and it has a huge success. And but we can also go from the other way around, that when we consider a system, well, so this background is kind of a very simple idea or motivation. like when we would like to solve this ODE system, and we need to compute like this matrix exponentials. But when this matrix has an eigenvalue decomposition form, and then it can make this matrix exponentials pretty easy and makes it simple. So to simplify this procedure lies on the fact that it needs like an eigenvalue decomposition which plays like a coordinate transformation. And similarly for these nonlinear systems, and we can also do something similar, and with the help of the Koopman operator. And this Koopman operator actually is a very also a very general concept. It shows that for a nonlinear but finite dimensional dynamic systems, you can transform it or its equivalent to a linear one or a linear system. But the price you pay is that you lift the system dimension from a finite dimensional to infinite dimensional problems. Therefore, there's with the Koopman operator that you can we can the Koopman operator do this transformation from nonlinear systems to linear systems. The key lies on the fact that we need to use the so-called observable functions. While the observable functions, by incorporating with the definition of the Koopman operator, it can make the dynamics evolution of the system from to be linear. And for linear problems, and it's easy to compute, also easy to control. And this framework works well when when the nonlinear system model F is unknown. Because we can go from this framework, so the upper row it goes from the upper row is just the evolution of the system states or the system dynamics of the original system. However, when the system model F is unknown, that it is difficult to predict the system dynamics. However, if we are able to transfer these nonlinear and unknown systems into the other coordinates, and we can perform the evolution of the dynamics through the Koopman operator. So the key lies on the fact is that we need to represent, or we need to construct the function g for this mapping. But since it's Koopman operator, it works for infinite dimensional case, and this makes this computational infeasible. Therefore, that we need to restrict the problem to a finite dimensional setting. So we need to focus on this invariant subspace of the Koopman operator, and then by introducing this invariant subspace, that we are able to compute infinite dimensional setting. So with this finite dimensional setting, and then it becomes easier to compute this Koopman operator. Well, in this case, the Koopman operator becomes the Koopman matrix. Suppose that right now we know we already have this setting. We already know this observable function g, and we are able to construct these two data sequences by using by just shift the time forward once. And so suppose that we have a few observed states of the previous of the original system, like from x1 to xp is the data that we could observe using some numerical by performing some experiments. And then we are able to construct these two data sequences, and then this Koopman operator and then this Koopman matrix, we can compute them by just solving this this equation. So for sorry. So then this problem is easier to be solved. but we do not really need to compute the pseudo inverse of one data sequence explicitly. We just need to compute them implicitly by performing some singular value decompositions. So the key for this framework lies in the fact that we need to find the representation of the function g that maps the original system states to a linear system setting. And the related work lies first that all the widely used engineering in engineering that they just called the exact DMD, or they just take the trivial map as a for the problem. Since well, this is not mathematically rigorous, but however it is widely applied in many engineering problems. And the later goes around with extended dynamic model decomposition, the extended DMD, and it predefines a set of basis functions or dictionary functions for this setting, and then using some learning methodologies to learn the coefficients. And similarly with techniques are the kernel DMD. Since the deep learning is gets more and more popular, and then going around the deep learning for this Koopman operator for the function g, for the learning of the function g. Also, there are many related works. So to summarize, the drawback of the current work is that for the Koopman operator learning, we would like to go from the original system states to the transferred system states from the G function. And then after this transformation, we are able to compute the Koopman matrix by using the sequence of the composed with G. And then after this computation, we are able to compute or predict the evolution of the GX series, and then we can go back by performing an inverse map of the sequence to get the predicted original system states. So this procedure is realized by this autoencoder network, and this autoencoder network actually it is like a one-way kind of approximation, since it can only like realize this approximation, like we have an x as an input, and then we encode it, and then we decode this to get an approximated output as an approximation of the original input. But this is like a one-way approximation, or like you have something here and you get something similar from the output, but the other way you cannot guarantee. Like you have you put something at the output, and you also would like to from the input side you have something similar with the input, but this is not achievable by the autoencoder framework. So we did some test that we train an autoencoder for this setting, and we test when the tested data are kind of far from the distribution of the training data, and the predictions may have chaotic behavior, or the prediction accuracy is very low. So when we check in detail that the issue to cause such phenomenon that this autoencoder is only one-way numerical invertible. It's not. It is not invertible in both directions. Therefore, if we can improve this case, we make this map invertible in both directions. Then it's easier to increase to improve the performance of this Koopman operator learning. Therefore, so we use the so-called affine complement functions to design such a network structure. And this affine complement functions, and it just like divides this input into two parts, and then when we transfer this information from one layer to the next layer, and then it just introduce keep part of the information and then use the other part for mixing, and then by introducing some nonlinear mappings, and then it can make this map to it then can make this map to approximate any nonlinear mappings, and by this setting and this forward direction is kind of is easily to prove the invertibility of the forward direction. Also for the backward direction, it's also easy to show both the forward and backward direction they are invertible. Therefore, for this simple setting, we can simplify the procedure for this Kopelman-operated learning in this part, and both the forward direction and the forward and the backward direction they share exactly the same network structure and also the same network parameters. Therefore, the training part or the computational part, the cost they can be much more reduced. Also, the loss function for this setting is that it can also be simplified compared with the you have 3 terms for the autoencoder, and for our setting we only need 2 terms, since this we only need two paths, and the first part it concerns with the reconstruction error, and the second part it just concerns with the approximation error of the Kopelman operator. So these 2 parts that can already guarantee or ensure us accurate results. So we have less parameters, and then it's easier to optimize, or it's easier to train this problem. So I just quickly go through these numerical results. So the first part is also a very simple, but also a benchmark problems used for the papers. And we compare it with a few other methods, and so our results is given by this red plot. And for the predictions, we can see that it can predict up to a relatively long time window without the error increasing too much. And also for similar. For the Burger's equation, and similar results also appeared, and also for different problems, and the performance is consistent compared with the other kind of methods. Okay, to summarize, the first one is that our resolution invariant deep operator network, we can train on low resolutions and predict for high resolutions. And it does not require the input domain and the output domain to be the same. And for the Kopelman operator learning, that the key lies in the fact of the observable function should be bijective, and this coupling flow invertible neural networks, it can guarantee this. And for the future work, I think we focus on the 2 parts. The first is that we are interested in the adaptive sampling for the training. Well, not only for the training, but also for the solution of the high-dimensional Bayesian inverse problems. The adaptive sampling also helps to reduce the computational cost. And the second part would be the real-world applications. It may make us to have new ideas to improve or to propose new architectures of the deep learning models. Okay, for the details of the talk, you can find in these 2 reference papers. Then I think I will be open for the questions.
Yeah, thank you so much, Yue. That was a really nice talk. Do we have any questions from the audience? Oh, there is a question in the chat. It says, have you tried the invariable method for noisy data?
You mean for the second part, or the
Yes.
I guess. Yes, I think. Yes, we tried a few experiments. Sorry that we did not report it in my talk. I think the noisy part, according to our experience so far now, is that so for this DMD computations, sorry, why I cannot okay, yes, for this DMD settings, because in theory the Koopman operator should be infinite dimensional, and then for the really computations we make it finite dimensional, and then we compute the Koopman matrix here. So for the real computations that we use the singular value decomposition of this matrix, and this matrix X also is composed of the observed data. And then often when we do this, we do the truncated singular value decomposition, and then the noise are often truncated by perform the first step. So our observation is that if the noise is not the noise ratio is not high, and then it works okay. However, if the noise ratio is high, and then this truncated SVD may introduce a huge error that cannot be kept in a low level.
Okay. Does that answer your questions, Bahadur? Yes. Great. Do we have any other questions from the audience?
You said that, I mean, your results also show that FNO is not the resolution invariant.
Yes. I mean, yes, I think especially for complicated problems, when we train with like the lowest resolution,
If you go back, can you go
yes.
back to another previous? You will see that you had the.
You mean this one?
No, the FNO. Just go back to the FNO. I was interested to see here, for example.
Yeah,
You see,
okay.
it's not resolution independent.
No, and actually, so this FNO that we did not introduce the hard constraint setting. However, even though we introduce the hard constraint, it cannot keep this prediction accuracy stable or
Yeah, because there is if you look at the chat, Channing put the second paper. Channing Chao
yes.
put this paper for you. That's the archive paper from Mishra's group that shows this is not that FNO is not discretization independent.
Yeah. Thanks.
You can look at that. That's yeah.
Great.
Okay.
Channing, do you have any questions for Yue?
Oh, I don't have questions. I just put the archive paper to the chat.
Thank you.
Okay. Great. It looks like we don't have any more questions. Once again, thank you so much, everyone, for your time today. Especially you stayed until 1 a.m. So thank you so much for that.
Actually, I really feel sorry because I can feel exactly that my brain almost stops. So
no, you did great. You did great. Thank you very much, Sheshia, and Wanan for staying late. Thank you.
Thank you.
Yes, thank you.
Okay, thank you so much, everyone, and see you next week in the next Scrum seminar. Have a good week, everyone. Bye.
Good. Thank you. Bye.